Good morning, ladies and gentlemen. My name is Avashna Govender, and today I will be presenting my work on model adaptation to generate synthetic child speech. So here is a quick outline of what my presentation today entails. So for those of you that are not familiar with speech synthesis, it is the artificial production of speech used for human-computer communication. And the system that synthesizes speech is called a text-to-speech system that takes text as an input and generates the corresponding speech automatically. So typically, your system will consist of two main components, your front end and your back end. Your front end receives the input text, and it does natural language processing on it. This means that it extracts linguistic information, which is required by the back end in order to generate your speech automatically. So here are just some applications of TTS. So TTS is useful for language learning applications and audiobooks, as discussed by the previous speaker, and is also useful for voice-enabled emails and SMS, and essentially any form of written text can be converted into speech automatically. But most importantly, TTS is useful for people that suffer with speech impairments that use assistive communication aids to communicate. For example, Stephen Hawking. So in speech synthesis, there are two common techniques that are used. The first is called unit selection. Unit selection is referred to as concatenative-based synthesis, which simply uses an inventory of natural speech samples that are recorded by a specific speaker. And this generally requires a lot of data, typically 2 or more hours of data. And the way that it works is, say for example, you have two words with the corresponding speech waveform recorded by a voice artist. And typically, these waveforms are segmented into smaller units called phonemes, which is your smallest unit of speech. And then at synthesis stage, say we want to synthesize the word tree, the backend will then go and look up the corresponding phonemes in the inventory and concatenate them to form the word tree. In this case, the first phoneme of train and the last phoneme of sea. So as you can see, with this technique, it works directly on your natural speech samples, and therefore it sounds really natural and is used in many of your commercial systems that exist today. For example, Siri on your iPhone, your Google TTS, Google Maps navigation, because companies like Google and Apple, for example, have lots of access to data. So that's why these systems sound quite natural. A more recent technique is called HMM-based synthesis, which is a statistical parametric approach. So essentially, it uses statistics to model speech and train a specific model. So the way that this works is that you'll have a database with recorded also by a voice artist that contains recordings and text. The recordings are used to extract information like your fundamental frequency and spectral features, and then linguistic information is extracted from your text, which is together used to learn a specific model. So this is the highlight of HMM-based synthesis, is that you are training a specific model, and therefore you need to know a little bit more about speech so that you can generate it completely from scratch, which is different from concatenative synthesis, which is just concatenating your natural samples in order to generate a new speech waveform. So here, once we have trained a model, that model is then stored, which is also an advantage because storing a model uses up much less memory than storing an entire database of speech samples. And then once we receive our input text, new models are then generated from these stored models and reconstructed automatically. So the type of model that we use in HMM-based synthesis is called a hidden Markov model, which is simply a finite set of states. So if you think of speech, for example, that's represented in the time domain, for instance, as shown on the right-hand side, we can then take this speech waveform and segment it into frames according to phonemes. And for each of these phonemes, a model is learned, and based on the training data and stored in the form of a probability distribution. So with HMM-based synthesis, your system typically requires roughly 2 to 5 hours of speech data. And it does produce natural speech, but obviously not as natural as in unit selection, because here we're using digital signal processing to generate the speech from scratch. However, with HMM-based synthesis, there's one major advantage in comparison to unit selection, and I will tell you why in just a few minutes. So, the reason why I decided to choose child speech synthesis is due to the fact that children with speech impairments that use assistive communication devices are currently forced to use these devices with adult voices that are usually American accented or British accented. And this is because there is no South African accented English children's voices available, and children's voices in general are not widely available. There's also very little research that is currently being done in the field of child speech synthesis, and I believe that these children deserve to have more appropriate speaker identities, a possibility that can be turned into a reality by synthesizing voices. So what is the problem? The problem with child speech synthesis is that there's a lack of data. And as you would have noticed in the previous slides, in order to develop a good quality speech synthesizer, we require a lot of data. So what do we do? One of the major advantages, as I mentioned, with HMM-based synthesis is that it has the flexibility to manipulate and modify its models. And this is called model adaptation. So basically what happens is we have an already trained initial model that has been trained with lots and lots of data, and then it's adapted to sound like a specific target speaker with only requiring a small amount of data from your target speaker. So for the rest of my presentation, I will be addressing 3 research questions that has been answered in my work. The first is, how should child speech data be collected and then synthesized and evaluated? And overall, the aim is to determine the most suitable approach to generate synthetic child speech that it makes use of the limited amount of data that we have available. So the first question is, how is child speech data collected? The problem with child speech data is it's very different from collecting adult speech data because we are faced with many problems. For example, finding volunteers who are willing to record their voices is difficult due to ethical issues. It is also more complicated to pay children for recordings like we can easily do for adult speech synthesis. Children also have a very short attention span, and therefore you cannot just put a child in a recording studio and expect them to record hours and hours of data. They also are not yet fluent readers. They read with hesitancy, repetition, and mispronounce their words. They also read with emphasis and expression, which leads to fluctuations in their voice, and these are all characteristics that are not suitable to train a TTS system. And here are 2 examples.
Antarctica is the continent of southern end of our planet.
Nectar is juice inside flowers.
Okay, so in my study, these are the following steps that we performed in order to collect child data, because as I mentioned earlier, there's no South African accented child data available. So firstly, we had to determine a target age group, and according to the literature, children's voices start to converge towards adults at the age of 11. So we had to choose children younger than this age. We then had to find children who are willing to and able to record useful data, and we had to take into consideration the level of fluency at which these children could read. We then identified suitable material at a level that was appropriate for children to read, which the easiest choice was children's stories, which we then selected text that contained phonetically rich sentences so that we could cover as many phonetic examples as possible, which is a requirement of building a synthesizer. We then set up a recording environment in a quiet office, and we recorded the child speech data. Here is a quick summary of the data that we collected. For the first session, we managed to record a girl aged 8 And this session took 8 hours with regular 30-minute breaks in between. And in total, we managed to collect 8 minutes of usable data. For the second session, we collected data from a boy aged 9, and halfway through the recording session, the boy refused to continue with the session, and therefore it was incomplete. We then had to find a third volunteer of a boy, so we found a boy aged 7, and because of the previous failed attempt, we decided to divide these sessions into 1 to 2 hours per day over a period of 3 days, and then collected 8 minutes of usable data. So in total, we collected 8 minutes from a boy child and a girl child. So as you can see, it is really difficult. So imagine trying to collect hours and hours of data. This can take a really long period of time. So once we have this data, the next question is, how do we synthesize child speech data? So we have our limited amount of data, and therefore synthesis becomes a really difficult task. The data that is collected is often too little and still contains minor imperfections. So what do we do? As I explained earlier, there's a technique called HMM adaptation that only requires a small amount of data from our target speaker. For instance, in adult speech synthesis, as little as 6 minutes of speech is required from our target speaker in order to develop a synthesizer that sounds like that target speaker. So is it possible to synthesize children's speech using HMM adaptation as well? Of course it is. But once again, it isn't a straightforward task. Because remember, in order to use this technique, we still require a lot of data to train that initial model that is used to adapt to our target speaker. And once again, we have insufficient data when it comes to child speech synthesis. So we then tried to adapt an already trained adult initial model to resemble a specific child target speaker. And this is how we do it. So we start off by having training data from adult speakers. So we used male speakers here and female speakers along with their text in order to build these initial models. And we use combinations of the speakers, and we varied the speakers and ended up with a model which is referred to as an average voice model. So this is what it sounds like.
After such a fall as this, I shall think nothing of tumbling downstairs.
Now, as you can hear, this model sounds quite weird, and the reason for this is because it's a mixture of male and female speakers. And this is sort of to take away the speaker dependence of using multiple speakers. Now, once we have our average voice model trained, we no longer need any of the training data, and the next goal is to try and adapt this average voice model to resemble our child speaker using our small amount of data of 8 minutes. And this is what our boy child sounds like.
The little daisy could not speak or utter a consoling word, much as it would have liked to do so.
So the way in which we adapt it to sound like this target speaker is by applying a transformation technique. So what the transformation technique does is it estimates certain statistics in the adaptation data in order to determine exactly how much we need to adjust this average voice model so that we can make it sound like our target speaker. And once we have applied our transformation technique, we then end up with adapted models, which we then use at synthesis stage, which produces our synthetic child speech, which sounds like this.
They learned from the sun and from its surroundings how kind God is. It did not mind that nobody saw it on the grass.
Okay, so in this study, as you could see from the adaptation process, there's two important things in this process. It's the average voice model and the transformation technique. So the next step was to determine which combination of techniques gives us the most natural and intelligible speech. So for our first experiment, we then played around with the different initial model configurations. So we built different initial models using only our male speakers and then female speakers and a combination of male and female speakers, which gives us 12 different configurations. For the second experiment, we then varied the adaptation techniques, and these adaptation techniques are combinations of each other and variants of each other based on two main techniques, which is maximum likelihood linear regression and maximum a posteriori. And from this, we ended up with 7 different configurations. So here's just a quick summary of all the voices that we ended up with. So for the first, we had our initial model with the different configurations, and we applied this speaker adaptation technique, which is the technique that has proven to work the best for adult speech synthesis. Once we found which of the initial models here performed the best, we then used it in the second experiment, and then we adapted the adaptation techniques in order to determine which adaptation technique produced the most natural and intelligible speech. So once we had this, we then had to determine how do we evaluate child speech. So typically, to evaluate synthetic child speech, you either perform objective or subjective tests. But at the moment, there's no single defined objective measure that is used to determine the quality of voice. So subjective tests tend to be a more popular technique. So in the study, however, we had to use objective testing because of the fact that we ended up with 12 with so many different configurations. So we had to reduce this test set to 4 voices. And in order to do this, we calculated the closeness between the natural and the synthetic speech by calculating the fundamental frequency and intensity, and in order to determine the closeness between our natural and our synthetic. And the 4 closest voices were then used in our subjective evaluation. So here is the results for our subjective evaluation, where we performed 3 tests. The first test is a preference test, where the listener was given 4 samples and had to select the sample that they preferred. The test on here is the naturalness test, where the listeners had to rate each of the voices on a scale from 1 to 5, 1 being the most unnatural and 5 being completely natural. And then the last test was an intelligibility test, where they had to transcribe the audio and write down only what they heard, and then the word error rate was calculated. So from here, you can see that the 2 models that had the lowest word error rate of roughly 22%, 22% performed the best. And at the same time, the male average voice model trained with 2 male speakers had the lowest number of votes in terms of preference, and it had the worst scoring in terms of naturalness. So from this study, we concluded that the mixed average voice model trained with 1 male and 1 female speaker performed the best. The same procedure was then repeated for the second experiment, and from here, this specific technique, CSMAP-LR followed by MAP, had the lowest word error rate, and it had the best score in terms of naturalness. But as you can see, it's still given a score of slightly natural, with only a few points in the range of natural and completely natural. So from here, we concluded that that technique was the best technique in the study. In addition to that, we decided to do evaluations with children, because children are our target audience. And so we decided to build an Android application that is more interactive and fun for the children to use. And then here are just some pictures of the children playing with the tablet and performing the evaluations. However, these evaluations, the results were inconclusive, because trying to control 40 children in a playground with trampolines and tablets can end up being really disastrous. So in conclusion, we managed to successfully collect child speech data, and we managed to synthesize the speech successfully using HMM adaptation. And in doing so, we determined that the gender mixed initial model in combination with CSMAP-LR and MAP transformation technique yielded the most natural and intelligible speech in the study. And also evaluating speech with the target audience is feasible, but we need to be able to do it in a more controlled environment. And for future work, we would like to explore more combinations of training speakers to see whether this results still hold. And also we would like to find an approach that is able to calculate the closeness between our training and our target speakers. Because our hypothesis is that if our training speakers are closer to our target speaker, then the naturalness will be improved. So our next work could possibly be to use teenagers as our initial model instead of adults and try to train that and adapt it to child speech. Thank you.
Thank you, Avashna.